Hi, this is Mrs. Lemke, and I hope you're having a really good summer. And this is the second of 4 review videos that Mr. Covey and I are making for you this summer. This one is about continuity and differentiability. We'd like to remind you that, of course, because you have the excellent benefit of being in a flipped classroom for math analysis, that certainly you already have access to a lot of materials on all of these review topics from the calculus part of math analysis. So if you get to the end of this video and you're like, oh, I don't really know if I know everything I'm supposed to know, feel free to access your math analysis notes and those videos to get some further review. So this is definitely going to be, I'm going to go through this kind of quickly because we're looking at this as a review, not as a first teaching. So understand that this is not necessarily indicative of the pace of the class that you're about to take. It is indicative of what review might feel like. So first of all, I just wanted to remind you about the 3-part definition of continuity at a point. So we say in a loose sort of way that functions are continuous if you can draw the function, draw a graph of the function without lifting up your pencil. That's not a rigorous definition, but it gives you an idea of what continuity means. If you are specifically interested in, is this function continuous at, say, x equals 4, then you would check these things at 4 or at a in general. So first of all, does the function actually exist at that location? So is there a point? Is there a value that is defined at that location? That's the first criteria. Secondly, does a limit exist as you get closer to that value from both sides? So in my discussion, I said something about at 4. So if we were looking at continuity of a function at x equals 4, we would look as the function goes towards 4 from the left and from the right. Do those two paths lead to the same location? And that's a limit existing. The left hand and the right hand limits exist and are the same. And the third thing is that both the answer to part 1 and the answer to part 2 have to match. So the limit as you approach a is the same as the function value at a. So sometimes I could refer to this as the 3-part definition of continuity, or the 3 pillars. And like any 3-legged stool, if any one of those does not hold true, the stool falls over, right? So all 3 of them have to be true. So now on this slide, I've included 3 pictures. This first picture, oops, sorry, I didn't mean to do that. This first picture over here is one that is definitely not continuous at 2. And so let's think about what part of the definition is violated. Okay, so first of all, does the function exist at that point? It does not. This is a hole. Okay, so this is the first pillar being violated. Okay, for example. In the second picture, I don't think I was very creative here, but in the second picture, it's the second pillar that's violated. I didn't really mix it up. So here you have the left-hand behavior coming towards 3. This time we're looking at 3. As you come towards 3 from the left and as you come towards 3 from the right, the limit here, the right-hand limit would be 4, but the left-hand limit would be 1, and 1 and 4 not the same. So this is the second pillar being violated. And here, this one is looking really good because you say, okay, I'm looking at whether or not this function is continuous at 2. And does f of 2 exist? Yeah, it does because it's right there. That's f of 2. F of 2 is 1.5. And does the limit exist? Well, yeah, because as you come from the left and you come from the right, you're going towards the same location right there. It looks sort of like it might be 1 or 0.8 or something like that. But those 2 things aren't the same. So this is the third pillar being violated. So I hope in seeing these 3 together, you can see why we do in fact need all 3 parts of the definition. It's not like you could just get by with 2 parts. All 3 parts matter. Okay, so I will read to you. Functions are continuous over intervals where the definition of continuity at a point is met for every value within that interval. So even though this definition is about being continuous at a particular location, generally speaking, we often will be more concerned about over what intervals is this function continuous. And then you just need to think about, well, is there any place in this interval where that 3-part definition wouldn't hold? Obviously, you're not going to check for every point because that would be an infinite number of points. That would be all you could get accomplished with the rest of your life. So let's not do that. So basically you can see here though that in this picture that has the blue and the red and the green parts all connected, that all of the, because it's all connected, that's what continuous means, right? And so all of these, all along this graph, points are defined, limits are defined, and the limit and the point are going to be one and the same. So piecewise functions, by virtue of being piecewise, aren't necessarily discontinuous, but they also aren't necessarily continuous. You have to see if the pieces actually connect, like the blue piece connecting to the red piece here. All right, so because it's easier to think about the odd cases, that kind of don't work out, even though we are often asked about where things are continuous, sometimes it's easier to think about where they are not continuous to answer that question. So my analogy to this is, my husband does a fair amount of the cooking in our household, and so he'll sometimes ask me, well, what would you like for dinner? And the thing is, I'm not a very picky eater, especially if someone else is going to cook. So I sometimes will say something like, oh, anything is fine except for, let's not have, burgers. I just ate, I ate red meat yesterday. I just kind of want to cut down on that or whatever. So sometimes it's easier to answer the question of what's for dinner by actually answering what's not for dinner. So same kind of thing. It's often easier to talk about continuity by saying where things are not continuous. And so things that aren't continuous would be things like jump discontinuities, holes, and vertical asymptotes. So with that in mind, before I explain what any of those are, I'd like you to pause this video. So actually pause it. Don't just like cheat and listen ahead. Okay, but I want you to pause right now, and on a piece of paper, and if you don't have a piece of paper, go get a piece of paper. On a piece of paper, I'd like you to draw just a little doodle for yourself of what you think I mean by each of those three terms on the screen right now. Okay, go ahead and pause. Okay, did you actually pause? Did you actually draw your three pictures? This is accountability to yourself, okay? So make sure that you've actually tested your own understanding. That's what this review is about. Okay, so here are some pictures. A jump discontinuity is, it doesn't have to look obviously like this exact example, but it should be something where you have a piece of a function that jumps to a different piece of a function, and that there's a gap in between, right? A removable discontinuity or a hole, just any graph at all that has a missing point in it, that point or that x value might be defined somewhere else, like this dot, but it might not be. It might just be a plain old, like a point is missing. And a vertical asymptote, this blue graph comes up and it comes down, but it has a value at which the function itself is not defined at all. And that's a vertical asymptote, or a non-removable discontinuity is what it's sometimes called, in contrast to a hole. Okay? All right, the other idea, that's kind of continuity. Differentiability is the other part of this video, and differentiability just means that the derivative exists. So you see here in black writing, f prime at x naught has to equal, and then this is our limit definition of the derivative. And I just noticed there's a weird equal sign in here, and I did not catch that when I stole this off the interwebs, so that's not good. That shouldn't be there at all. Okay, that little equal sign. Sorry about that. So f prime at x naught is defined to be this limit. Okay, that's your difference quotient limit, and your alternate definition would also work there, okay, if you had that. But basically it's just saying a function is differentiable at a location if the derivative exists at that location, okay? So don't overthink that. That's all differentiability means, the derivative exists there. And similar to what we said for continuity, if you have an interval over which every value in that interval meets this definition of differentiability, the derivative exists everywhere in that interval, then you say that the function is differentiable on that interval. This is a key slide, okay? So differentiability tells you that the function has to be continuous, because if I say a function is differentiable on an interval, that means that the function had to exist everywhere in that interval in order for the derivative to be able to be taken, okay? So if I so if I say that differentiability implies continuity, if I say something is differentiable, let's say from 1 to 7, then that means that the function itself had to be continuous from 1 to 7, okay? Because if there was an asymptote, then there couldn't be a derivative at that vertical asymptote. Or if there were a hole, there couldn't be a derivative at a point where the point isn't even there. Okay, so that's really important to understand. Differentiability is a powerful statement because it tells you continuity. However, my saying continuous doesn't mean you have differentiability, because there are graphs that are full on continuous, but the slopes aren't well defined. Even though the graph is well defined, the slopes aren't well defined. So again, I'm going to ask you to pause. Try to draw some graphs that are continuous, but not differentiable. What are some problems that can come up in terms of defining slope on a continuous graph? Okay, do you understand the task? The task is to try to draw some functions that are continuous yet not differentiable. What sort of problem shapes can you make? Okay, pause the video, draw, and come back. Okay, how many pictures do you have? I hope certainly more than one. Let's see. I have some pre-set up pictures here. So a corner is a problem location, a cusp would be a problem location, and a vertical tangent line would be a problem location, as well as anything that lacks continuity. But what I asked you to do is to draw things that were continuous but problematic, okay, for the derivative existing. So a derivative doesn't exist at a corner because we can't well define what a tangent line would look like at this corner. Same thing here, we can't well define what a tangent line would be at that kind of shape, and the only distinction between these two vocab words has to do with whether you have straight line segments meeting, then we say corner, or if we have curvy kind of chunks of graph meeting, then we say cusp. Vertical tangent line is what it sounds like. It's a line that is tangent to the graph, yet the line itself is a vertical line, and vertical lines have undefined slope, and since derivatives are slopes, that means that the derivative isn't defined there. All right, the last thing I want to show you is a link that I'd like you to type into your computer, and I'd like you to go to this website. I was going to make a bunch of questions for you, and in searching for problems to use, I happened upon this excellent website that has all these great questions. So this is not something that Mr. Covey and I can check up on and see if you did. We're not going to. This is your responsibility, okay? So to see if you understand continuity and differentiability, you can go to this website. You'll see what I screenshotted here in purple, and just do the questions. And then at the bottom, or actually along the way, it has a lot of different things where they say check and see how you're doing. If you get most of this right or all of it right, great, you're done. You don't need to worry about continuity and differentiability in terms of your review. However, if it goes poorly, listen to this video again, try the problems again, and or go back to your math analysis videos on continuity and differentiability just for a little refresher, because we want you to start the year out strong and on the right foot. Thank you so much for listening to this, and I can't wait to see you guys. I look forward to having you listen to the other two videos as well. Thanks.